The screen opens upon a vast cosmic panorama, rivers of starlight flowing across an ocean of darkness. Nebulae burn like slow embers, galaxies drift like frozen storms, and behind them all, a silence older than memory. Through that silence, a single photon travels, born perhaps 13.5 billion years ago, a survivor from the universe's dawn. It drifts across eons of expanding space until, at last, it meets a mirror of gold suspended in the void, the James Webb Space Telescope. A voice rises through the darkness, measured, calm, searching. We are time travelers. Every glance into deep space is a journey backward. But what if, in that journey, we glimpse something that should not exist? Something older than the beginning itself? A montage unfolds, mirrors unfolding like petals of light, detectors cooling to near absolute zero, streams of data descending to Earth. Scientists lean toward their screens, eyes lit by the ghostly glow of numbers. Then, a flicker, an anomaly, a single red dot, almost invisible, hiding in the noise. If the object is real, it challenges everything. By our equations, it should not be there. Its light is too old, too distant, too early. Either our instruments deceive us, or the cosmos does. The question emerges, sharp and unshakable. What if the universe did not begin the way we thought? Humanity's oldest wonder, where did we come from, now collides with the cold precision of cosmology. The voice softens, almost reverent. Tonight, we follow that single red dot. We trace its light, its meaning, and perhaps we will discover that the beginning itself is more mysterious than we ever imagined. It began with a mirror unfolding in the silence of space, a slow awakening of gold and light. A machine built not just to see farther, but to look deeper into the memory of existence itself. The James Webb Space Telescope was humanity's most audacious, an observatory suspended beyond the warmth of Earth, its golden petals unfurling against the eternal black. Each hexagon, a promise carved from mathematics and faith. It was December 2021, when Webb slipped from the planet's gravity and began its month-long voyage to the L2 point, a gravitational stillness 1.5 million kilometers away. There it would rest in frozen equilibrium, guarded from the sun by a 5-layer veil, thinner than whispers and colder than anything on Earth. When the first light entered its mirrors, scientists did not cheer immediately. They waited, because this telescope was not built for spectacle, but for revelation. Its eyes could see what human sight could not: infrared waves that carried the oldest light in the universe, light so stretched by time that it had faded beyond the reach of Hubble. As Webb's instruments cooled to near absolute zero, the first photons arrived from a realm older than galaxies. The JDs and Sears programs, early, deep field surveys, began their silent work. They aimed not at the familiar stars of our age, but at the cosmic dawn, the epoch when the first galaxies were born. What Webb revealed was not what astronomers expected. In its earliest images, tiny, red smudges appeared in the darkness, faint and ancient. Each one a fingerprint of a galaxy billions of light years away, but some glowed too brightly, their redshift too high, their light too old for comfort. These were not the soft embers of infant galaxies. They blazed like mature cities in a universe barely awakened, objects that by all accounts should not have existed yet. They were called universe breakers, galaxies that defied the age of the cosmos itself. Some lay at redshifts beyond 10 or 12 their light emitted when the universe was less than 300 million years old, and yet their structures suggested age and weight. Their masses rivaled those of galaxies that should have taken billions of years to form, and their spectra hinted at heavy elements: iron, carbon, oxygen, born from multiple generations of stars that could not have lived and died so quickly. In the control rooms and data labs of the world, scientists stared at the pixels in disbelief. Across screens in Baltimore and Leiden in Colorado, and Cambridge, small points of red rewrote the meaning of time. Among those who led the charge were Joel Lager and Erica Nelson, who passed the first data sets of distant galaxies, Rohan Naidu, Peter Van Dokkum, and their teams whose models sought to anchor these red smudges to known physics. Their nights blurred into weeks, testing every calibration, every background subtraction, every assumption that could twist light into illusion, knew how easy it was for light to deceive a dusty galaxy nearby, could masquerade as a distant one. A calibration offset could shift a redshift. A single unflagged error could create a phantom from noise. Yet with every test, repeated the anomaly, persisted in. The summer of 2022, the first papers began to appear in preprint archives. They spoke carefully, almost apologetically, of galaxies so luminous, so massive, so early that even the LCDM model, the foundation of modern cosmology, strained to contain them. The findings came from Webb's near-infrared camera, NIRCam, a lattice of detectors tuned to capture wavelengths invisible to human eyes. By measuring the redshift, the stretching of light caused by the universe's expansion, astronomers could place each object on the cosmic timeline. But when those redshifts implied ages too close to the birth of time itself, the data became something else entirely, an accusation whispered against the Big Bang's chronology. The papers detailed their methods: stellar population synthesis models, mass-to-light ratios, luminosity, functions, each parameter tested, each uncertainty listed, but the implication was impossible to ignore. If the data were right, then these galaxies existed when the universe should have been dark and silent, before stars, before chemistry, before structure. The news spread quickly. Beyond the journals, headlines declared that the Big Bang was in trouble, that Webb had seen the impossible. The phrase "older than the Big Bang" began to circulate, a simplification, but one that captured the public's awe and the scientific unease beneath it. Skeptics urged caution, reminding that photometric redshifts can mislead, that early estimates often collapse under spectroscopic scrutiny. But even they admitted that something extraordinary was unfolding, that the universe, once again, had outpaced human imagination, and so, amid the noise of headlines and the quiet of laboratories, a single image began to define the new frontier. A red dot in a sea of black so faint it bordered on illusion, and yet so provocative, that it seemed to whisper of a time before beginnings. That dot, perhaps a galaxy, perhaps something stranger, would ignite a question more profound than any telescope had ever asked. Could there be light older than the dawn itself? The first rule of cosmology is humility. Every discovery begins as a whisper from the deep sky and ends with a reminder that the universe does not owe us comprehension. When the faint red galaxies from Webb's first deep fields appeared, astronomers did what they always do. They measured. The light was stretched, its wavelengths lengthened by billions of years of cosmic expansion redshift. They called it the universe's signature of distance and time. The greater the redshift, the farther and older the source of that light. To measure redshift is to read the autobiography of the cosmos, each spectral line a letter, written in hydrogen and helium, each color shift a record of the universe's breathing at a redshift of 10. The light comes from an epoch when the universe was scarcely 500 million years old. At 12, it is younger still, perhaps 200 million years after the Big Bang. But some of the points found in Webb's early surveys whispered of even greater distances, redshifts beyond 13, beyond the theoretical reach of galaxies themselves. Their light was ancient enough to graze the first shadows after the birth of time. To see them was to stare toward the horizon of creation and find not emptiness, but structure, mass, stars, and chemical fingerprints that should not yet exist. If these galaxies were real, if their distances were confirmed, then their existence would fracture the accepted timeline of the cosmos. Because the Big Bang model, the LCDM framework that defines modern cosmology, leaves little room for such maturity so early in that model. The early universe was a smooth plasma of light and particles, hydrogen, helium, and a trace of lithium drifted in a sea of radiation. It took nearly 380,000 years for the universe to cool, enough for atoms to form and hundreds of millions more for the first stars to ignite. Only then, under gravity's patient hand, could galaxies coalesce, small ones first, merging slowly into giants across billions of years. Yet, the Webb images told a different story. In its mirrors appeared compact galaxies whose brightness defied reason. Each was so luminous that it suggested not a first generation of stars, but several. Stars that had already lived, died, and seeded their surroundings with heavy elements. Iron and carbon, products of supernova, flickered in their spectra. But there had not been enough time for so many cycles of birth and death. The arithmetic of cosmic history no longer added up. The paradox was stark either. Galaxies had formed, evolved, and enriched themselves in a fraction of the expected. Time or something far deeper was wrong. Perhaps the physics of the early universe itself was incomplete. Perhaps new forces or unknown forms of matter had accelerated creation's pace. The standard cosmological model describes a universe woven from dark matter and dark energy L. The cosmological constant drives its expansion, while cold dark matter builds the scaffolding upon which galaxies grow. In this model, structure forms hierarchically. Small clumps merging into larger halos, gas cools, stars ignite, supernovae enrich the medium, and galaxies evolve. It is an elegant model, consistent with the cosmic microwave background, galaxy surveys, and gravitational lensing, but the Webb data strained that symmetry. The too early, too massive galaxies suggested a cosmos that builds faster than physics permits for a galaxy to reach. Such mass within 200 million years its stars would need to form at impossible rates, hundreds of solar masses per year in a universe barely born. Cooling times for primordial gas clouds would need to be drastically shorter, and star formation efficiencies many times higher than current theory allows. Some galaxies showed signs of being compact, yet massive, others luminous beyond expectation, and some even displayed hints of metals, the heavier elements forged in stellar cores. These fingerprints implied that generations of stars had already come and gone, but by the cosmic clock, there should not have been enough time for even one full cycle. This became known as the paradox of maturity. How could galaxies so young appear so old? How could the universe, still shrouded in the fog of Ryanization, host such brilliance? Some astronomers compared the data to finding an ancient forest blooming before the soil had formed. Others called them illusions, artifacts of calibration, misread colors, the tricks of dust or lensing for the LCDM model to survive untouched. These galaxies must somehow be imposters. Perhaps their redshifts overestimated by dust-obscured starlight. Perhaps gravitational lensing had magnified nearer galaxies, fooling the measurements, or perhaps spectral noise had been mistaken for the Lyman break. The telltale drop-off of ultraviolet light redshifted into the infrared in labs and offices across the world. Teams began to cross-check the results. They ran simulations, recalibrated instruments, reanalyzed the photometric catalogs. Some reminded their colleagues that history was littered with false alarms. In the early 1990s, astronomers once announced quasars older than the universe, a claim that dissolved under better data. The cosmos had embarrassed human certainty before, and it might again. Still, the unease lingered because even after layers of skepticism and refinement, some of Webb's targets remained stubbornly inexplicable. Science advances by doubt, but also by wonder. And here, both forces were entangled. The scientific community split into cautious camps. Some urged restraint. The data were young, the instruments still being calibrated. Others whispered that perhaps it was time to rethink the beginning itself. Peer reviewers demanded more evidence. Spectroscopic confirmation, not photometric inference. They wanted lines, oxygen, hydrogen, carbon, signatures etched into the spectra that no dust could mimic. Only those would decide whether these galaxies were genuine messengers from the dawn. Yet even without confirmation, the question had already broken free of equations. It carried a philosophical weight, for if these galaxies truly existed in an epoch when matter should have been formless, then the narrative of cosmic genesis itself must bend the idea of a sudden birth. A single bright instant, giving rise to all, might need to yield to something subtler. A universe that gestates in layers, or perhaps one that recycles its own beginnings as months passed. Teams prepared deeper observations. Our spec instruments were tuned to capture spectra of the most extreme candidates. If even one of them proved real, cosmology would face its first genuine fracture in decades, and beneath the mathematics and peer reviews, lay a quiet recognition that this was more than a technical problem. It was existential, for to question the timeline of the Big Bang is to question the story that has defined cosmic order for a century. Science has always lived at the edge of contradiction, but seldom does the contradiction stare back from the deep sky so vividly as those red smudges, tiny, silent, and impossibly old, flickering in the mirror of a telescope that may have seen farther than the universe itself intended. It begins in silence, the deep, patient silence of a telescope listening across eternity. When the James Webb Space Telescope first spotted the crimson smudges that seemed to predate known cosmic history, the world gasped, but the astronomers did not. They paused. They knew the difference between a whisper and a hallucination. The universe, after all, is an expert at illusion. To understand the truth of any distant light, one must first decode its color. Photometric redshifts, those first, broad estimates, are like glances through fog. Light measured across wide bands, compared against theoretical spectra, and interpreted through complex models. But it is only with spectroscopy, with instruments like JWST's NIR spec, that the fog begins to part. In spectroscopy, every photon is stretched across the prism of time. The spectral lines, thin, ancient fingerprints of hydrogen, helium, oxygen, tell astronomers not just how far away something is, but when it truly was. The Lyman alpha line, in particular, is the cosmic boundary marker. It drifts redward as the universe expands, a measure of the universe's breathing. Yet the task is brutal. These galaxies are faint, their light barely distinguishable from background noise. The detectors must stare for dozens of hours, collecting photons that left their source when the universe was only a few 100 million years old. Even then, confirmation is elusive. Foreground interlopers, dust clouds, faint stars, chance alignments mimic the signals of the ancient. Sometimes, what seems like the dawn of time is only the echo of something far closer, masquerading through dust. The researchers move slowly, meticulously, cross-checking each signal. They search for telltale spectral breaks, abrupt shifts that reveal the absorption of high-energy photons by primordial hydrogen. When those breaks align perfectly with theoretical predictions, confidence grows. When faint emission lines of oxygen or carbon flicker within the noise, a deeper mystery begins to take form. Spectroscopy turns the photograph into a confession. It either confirms the ancient age or exposes the illusion. And as the first spectroscopic confirmations came in, the illusion did not fade, it deepened. The investigation expanded beyond the boundaries of Webb's golden mirrors. Other instruments joined the search, each tuned to a different language of light. The Atacama Large Millimeter Submillimeter Array, ALMA, on the high deserts of Chile, began hunting for the soft radio whispers of cold dust and molecular gas. These signals trace the raw material of stars, the scaffolding of galaxies. When ALMA detected oxygen in a galaxy known as JWST Z14-0, existing a mere 280 million years after the Big Bang, it suggested something astonishing. Heavy elements, forged in the hearts of stars, already existed. But that should have been impossible. For oxygen to appear so soon, several generations of stars must have lived, burned, and died, each cycle taking millions of years. That enrichment should not have had time to occur. Yet there it was, written in the spectrum, a chemical signature of maturity in a cosmic toddler. Astronomers began layering the data: infrared from JWST, submillimeter from ALMA, optical from the VLT and Keck. Each wavelength offered a new perspective, like viewing the same ancient painting under different light. They modeled the galaxy's spectral energy distributions, fitting them against stellar population templates. Dust models and star formation histories. Some galaxies, like MOEM Z14, appeared to exist only 280 million years after the Big Bang, sooner than theoretical cosmology allows. Others showed star formation rates 100 times greater than those of galaxies a billion years later. Patterns began to form, a constellation of anomalies. These galaxies were not isolated curiosities. They seemed to belong to a broader class of early overachievers, each one straining against the cosmic timeline. They were too massive, too luminous, too chemically evolved. The standard model, LCDM, predicts that galaxies should assemble gradually through the slow merging of dark matter halos, cooling of gas, and sequential star births. Yet these young universes already looked old. If confirmed, these galaxies would represent a deep wound in cosmology, a place where the universe's established narrative begins to unravel. But science, by its nature, demands skepticism. Each extraordinary claim must survive 1,000 small deaths by scrutiny. Some of the early candidates failed the test. When spectroscopic follow-up was performed, certain red smudges that once seemed to hail from cosmic dawn revealed themselves to be imposters, dusty galaxies or quiescent giants billions of years younger than expected. Their redness was not the mark of ancient expansion, but of internal obscuration. Others were contaminated by noise, or their fluxes overestimated due to lensing effects. Light magnified by intervening clusters of galaxies, distorting the true brightness and inferred mass. Still, after the illusions were stripped away, a core of undeniable evidence remained, a population of galaxies existing far earlier than theory anticipated. Discrepancies deepened as astronomers compared different methods of measuring mass and age. Stellar population fittings suggested enormous stellar masses, billions of suns condensed within mere hundreds of millions of years. Yet dynamic models, based on observed velocity dispersions, sometimes yielded smaller values. The two approaches rarely aligned perfectly. The tension was statistical but persistent. Even if some galaxies were overestimated, the sheer number of extreme cases implied that something fundamental might be missing from our cosmological equations. Some theorists began to explore new frontiers. Non-standard dark matter models, variations in the baryon to photon ratio, or early bursts of star formation triggered by exotic physics during cosmic inflation. Others invoked population 3 stars, the first, metal-free beacons of the universe, burning far hotter and shorter than any modern star, seeding early enrichment in a fraction of the expected time. Yet none of these explanations fully resolved the paradox. For every candidate explained away, another appeared just beyond reach, slightly fainter, slightly older, slightly more impossible. The deeper astronomers looked, the more the pattern expanded, like cracks spreading beneath the varnish of a masterpiece. By 2024, the number of high redshift candidates exceeded what LCDM simulations could comfortably reproduce. The theoretical universe, built over decades of precision data from WMAP and Planck, began to feel constrained, stretched thin by the growing weight of observation. It was as though the cosmic dawn was brighter, faster and more fertile than the universe should have allowed. At conferences, quiet conversations turned speculative. Were these galaxies genuine heralds of new physics, evidence that the early universe evolved differently, or that our measurements of time itself might be skewed by unknown factors? Or were they simply the limits of human perception, our instruments reaching the edges of certainty where noise masquerades as revelation? The answer, as always, lay not in belief, but in persistence. Astronomy advances through paradox, the uncomfortable dissonance between what is seen and what is known. The Webb telescope, in its quest for origins, had not shattered the Big Bang. It had done something more profound. It had restored mystery to a cosmos that once seemed fully mapped, and as new data poured in, each photon carrying the memory of a time before stars, scientists found themselves standing once more on the threshold of wonder. The light that had traveled for 13 billion years was not done speaking. It was only beginning to whisper. At first, the discoveries were isolated, a few crimson sparks at the farthest reaches of sight, statistical curiosities perhaps, or errors waiting to be corrected. But then, the pattern began to spread. Galaxy after galaxy emerged from the darkness, each one whispering of an age too early, of stars that should not yet have burned. Within a single year of James Webb's first observations, astronomers reported structures existing a mere 250 million years after the Big Bang, the so-called universe breakers. They appeared massive, billions of solar masses, and mature, their starlight rich with the signatures of heavier elements. In the cosmic calendar, they stood where theory predicted only hydrogen fog and scattered ionized gas. Each new detection shifted the boundary of possibility. The cosmic frontier, once thought to be fixed at a comfortable distance, moved inward, closer to the beginning. The deeper the telescope peered, the more the early universe filled with light, organized, structured, and astonishingly busy. The data were not quiet anomalies anymore. They were a chorus. If even half of these galaxies were genuine, something fundamental was wrong with the story written into cosmology's foundations. Perhaps this was not an error of observation, but a flaw in the timeline itself. Perhaps the clock by which the cosmos had been measured for a century was not keeping time correctly. Astronomers began to speak in cautious tones. The word impossible was retired, replaced by unexpected. The early universe, once imagined as a slow awakening, now looked like a blaze igniting before the dawn. To accept these galaxies as real is to rewrite the sequence of creation. In the standard LCDM model, matter forms gradually. After the Big Bang, there is a long silence, about 380,000 years, before light can move freely, marking the birth of the cosmic microwave background. Then, for nearly 100 million years more, darkness reigns. In that darkness, gravity gathers cold hydrogen into clumps. The first stars flicker to life perhaps 150 million years after the beginning. They are massive, short-lived and primitive, fusing the first traces of helium into carbon and oxygen. Slowly, they seed the universe with complexity. But Webb's data suggests that by 200 million years, galaxies already shone with structured light, stars of multiple generations, metals in abundance, possibly even dust and organized rotation. It would be as though the universe leapt ahead by hundreds of millions of years, compressing epochs of formation into a cosmic instant. If true, it changes everything. The epoch of reionization, the grand turning point when the first light reionized the hydrogen fog, would have begun far earlier. The seeds of galaxies might have been planted before recombination itself, through unknown processes or fluctuations beyond the reach of current physics. Some theorists propose that density variations from inflation might have been more extreme than predicted, creating pockets of early structure. Others speculated that dark matter, usually slow to collapse, might interact more efficiently than assumed, catalyzing rapid formation. Still others asked a more radical question. What if the cosmological parameters derived from the cosmic microwave background, the very numbers that define our understanding of time, expansion and age, were slightly off? Even a small deviation in the Hubble constant, or the ratio of matter to dark energy, could alter the inferred timeline by tens of millions of years. Yet those parameters have been measured with exquisite precision by missions like WMAP and Planck. The conflict between them and Webb's findings created a tension, not just scientific, but existential. For cosmology, this was not a mere puzzle. It was an identity crisis. At the heart of the modern universe stands a single equation, the LCDM model. It describes how space expands, how matter clumps, how the cosmos cools and structures rise. For decades, it has fit observation with astonishing accuracy. From the temperature ripples in the CMB to the clustering of galaxies, from the shape of the cosmic web to the acceleration of expansion. But LCDM is not sacred. It is a construct, mathematically elegant, empirically tuned, and as fallible as the humans who made it. Now, faced with galaxies that seem to exist too early, the model quivers. If stars could form, merge, and enrich themselves faster than LCDM allows, something essential must be missing. Perhaps dark matter does not behave as cold and collisionless as assumed. Perhaps it interacts weakly with radiation or baryons, accelerating the formation of the first halos. Perhaps cooling channels in primordial gas, enabled by molecular hydrogen, turbulence, or even exotic physics, were far more efficient than our simulations predict. Or perhaps inflation itself, the brief, superluminal expansion that set the initial conditions, was more chaotic, leaving denser seeds where galaxies could gestate almost immediately. To entertain such ideas is not heresy. It is the process by which science breathes, yet the implications are vast. If the universe built itself faster than our equations allow, it may mean the constants we hold sacred, OM, H0, S8, are only approximations of a deeper truth. It may mean that cosmic time, as reconstructed from background radiation, is subtly curved or stretched by phenomena we have not yet perceived. Some even whisper that we might be glimpsing physics from before the Big Bang itself, remnants of a prior cycle, or quantum echoes leaking through the boundary of inflation. Such speculation remains fragile, grounded in neither evidence nor consensus, but the very fact that it is spoken shows how deeply Webb's images have unsettled the modern cosmological order. When galaxies appear where they should not exist, the universe itself becomes a riddle, and the equations that once felt like scripture begin to sound like poetry. Beautiful, approximate, and unfinished. In the quiet corners of observatories and conference halls, the mood has changed. There is excitement, yes, but beneath it, a strange vertigo. For generations, cosmologists believed they were converging on truth, a single coherent narrative stretching from quantum foam to human eyes. Now that narrative trembles. Every new data release feels like a challenge to the foundation. Some scientists embrace the uncertainty, their curiosity ignited by the scent of revolution. Others retreat into caution, unwilling to rewrite the cosmos until the evidence is incontrovertible. The tension is not only intellectual, but emotional. Behind every graph and spectrum lies a career, a reputation, a lifetime of theoretical work that may now hang in the balance. And beyond the scientific community, the media watches with hungry eyes. Headlines cry out, "Did the Big Bang fail?" Or "James Webb proves the universe older than time." But inside the field, the language remains careful, almost reverent. The words tension and anomaly replace disproof. Scientists know that data can deceive, that what looks like a revolution may one day settle back into harmony with the old models. Yet, they also know that sometimes the universe whispers something genuinely new. When the Hubble Deep Field first revealed thousands of galaxies in a single patch of darkness, it expanded humanity's sense of scale. Webb, by contrast, seems to be expanding our sense of origin, showing us that creation may have been more immediate, more complex, and more mysterious than any equation can capture. In this twilight between certainty and discovery, cosmologists find themselves humbled. The farther they look, the less they seem to understand, and yet the more they feel the pull of wonder. The mystery does not end in contradiction, it deepens into awe. The light from the universe's first dawn continues to arrive, ancient, red, and trembling. And as it reaches the mirrors of Webb and the minds of those who study it, it carries a quiet message across the void. That even now, after all our models and measurements, the cosmos is still becoming known. And its first story may be older, faster, and more magnificent than anyone dared to believe. When the data began to defy the timeline, theorists returned to the first principles, the birth of structure itself. Perhaps, they proposed, the early universe was not as patient as once believed. In the immediate aftermath of the Big Bang, matter was not evenly spread across the newborn cosmos. Tiny fluctuations, quantum ripples inflated to cosmic scales, seeded the web of galaxies. But if those initial ripples were slightly stronger in certain regions, matter could have collapsed faster, denser, and earlier than expected. Simulations began to explore this possibility. Regions where overdensities were high enough that gravity overcame expansion sooner. In such privileged zones, clouds of primordial hydrogen might have cooled and condensed within a few tens of millions of years after recombination. Cooling was the key. In the young cosmos, gas was almost pure, hydrogen and helium, with no dust, no heavy elements to radiate away heat. Under standard physics, this should delay star formation. But if exotic cooling mechanisms operated, perhaps through trace molecular hydrogen, or early forming molecules like HD or lithium hydride, the gas could lose energy faster, fragmenting into smaller, denser pockets. Those fragments could ignite the first stars earlier than models predicted. Colossal population 3 giants, hundreds of times the mass of the Sun, burning hot and dying young. Their supernovae would scatter heavy elements into the surrounding space, enriching it for a second generation of stars. Those Webb might now be glimpsing. In this view, the universe did not cheat its timeline. It simply worked more efficiently than humans had assumed. The physics of collapse, once thought slow and stately, might have been frantic and improvisational, a cosmic shortcut written into the density of the primordial fog. Yet this explanation, though elegant, demanded fine-tuning. It required the earliest gas clouds to collapse with extraordinary precision, the cooling to proceed without disruption, and the resulting galaxies to assemble with near-perfect timing. It answered some questions, but left a larger one untouched. Why would so many regions follow this improbable path at once? The mystery deepened. Another idea began to surface, one far older and far stranger. What if the first structures were not made of stars at all, but of shadows? In some models, black holes could have formed in the first instance after the Big Bang, not from dying stars, but directly from density fluctuations in the primordial plasma. These so-called primordial black holes could range from microscopic grains to objects weighing thousands of suns. If they existed, they might have served as gravitational seeds, anchors that pulled in surrounding gas and dark matter, catalyzing the birth of galaxies long before ordinary stars could form on their own. A primordial black hole of just a few thousand solar masses could, in theory, gather enough gas to create a compact, luminous protogalaxy by the time Webb's red galaxies began to shine. They would act as invisible scaffolds, speeding up the process of cosmic structure formation by orders of magnitude. But this elegant shortcut comes at a price. If primordial black holes were too abundant, they would distort the cosmic microwave background, gravitationally lens distant light, or disrupt binary stars. Surveys like Ogle and Eros have placed tight limits on their abundance through micro-lensing constraints. The Planck satellite has ruled out large populations of them across many mass ranges. Still, a small population could have slipped through the cracks, rare enough to evade detection, but influential enough to reshape the first few 100 million years. Such an idea bridges the smallest and largest scales of reality. Quantum fluctuations that collapsed into black holes in the first fraction of a second could later sculpt the cosmic web itself. It is a theory both thrilling and disquieting. That darkness, not light, may have built the first cities of stars, and it leaves open a haunting question. If these primordial seeds exist, are they still out there, hidden within galaxies, silent witnesses to the universe's first heartbeat? If neither early collapse nor ancient seeds can fully explain the observations, the answer may lie in the invisible majority of the cosmos, dark matter. In the LCDM model, dark matter is cold. Its particles move slowly, clump efficiently, and dominate structure formation. But if it were slightly warmer, moving faster in the early universe, it could have changed the pace of cosmic growth. Warm, dark matter suppresses small-scale structures, delaying galaxy formation. But certain variants of self-interacting or decaying dark matter could have the opposite effect, enhancing early collapse. If dark matter particles occasionally collide or exchange energy, they can dissipate heat like ordinary matter, forming denser halos sooner. These halos could have drawn in gas earlier, triggering star formation before standard physics permits. Some models propose dark matter that decays over billions of years, releasing energy into the early universe and altering its thermal history. Others suggest it interacts faintly with photons or neutrinos, modifying how density ripples evolved after inflation. Each variant reshapes the cosmic clock in subtle ways that might bring theory closer to Webb's data. But these are radical departures. They imply that the invisible scaffolding of the universe behaves differently than we've believed for decades. Every alteration must still fit the constraints of the CMB, large-scale structure, and gravitational lensing observations. Yet even the most conservative physicists now admit, if Webb's galaxies are real, and as old as they seem, something in the dark sector may not be as simple as cold and collisionless. The unseen majority of the universe might be whispering through the earliest light. Beyond individual mechanisms lies a grander possibility, that the entire framework of cosmic history may be incomplete. Some theorists have turned to early dark energy, a form of vacuum energy that briefly dominated the universe before fading away. If true, it could accelerate the formation of structures earlier than expected, while still matching today's cosmological data. Others look to phantom energy or dynamic vacuum fields, in which the density of dark energy evolves with time. Such variations could stretch the timeline, allowing light from the earliest galaxies to appear older or more mature than they truly are. But beyond these refinements lies an even deeper heresy, that the Big Bang may not have been a singular beginning at all. In cyclic or bouncing universe models, what we call the Big Bang is simply a rebound from a prior cosmic contraction, a phoenix moment in an eternal sequence of expansions and collapses. If traces of that prior universe survive the bounce, quantum imprints, density patterns, or black holes, they could act as seeds for early structure in our own epoch. In this view, the impossible galaxies might not violate physics at all. They could be fossils from an earlier cosmic era, carried across the boundary of time, like ancient spores in the soil of a new world. Another frontier lies in the multiverse hypothesis, the idea that our universe is one bubble among countless others, each with its own physical constants and expansion history. If two such regions ever interacted, or if our observable cosmos is part of a larger, uneven landscape, the light we see might carry mixed signatures from neighboring domains. Perhaps some of the galaxies Webb observes were born in a slightly different vacuum state, where time flowed at a subtly different rate, and now appear older than our universe should allow. Speculation, yes, but not fantasy. The mathematics of inflation, quantum fields, and vacuum decay all leave room for such complexity. Reality, at its deepest level, may be more like a foam than a line, bubbles of existence forming, merging, and collapsing in an infinite sea of becoming. The galaxies that seem older than time may simply be reflections of that larger, untamed cosmos beyond the limits of our horizon. Revisiting the Big Bang itself, every theory returns, eventually, to the same haunting question. What if our very definition of the beginning is flawed? The Big Bang is not a point in space. It is a boundary in time, a surface beyond which the mathematics of general relativity breaks down. We call it the birth of the universe, but perhaps it is only the first visible frame of a film that began long before the light reached our eyes. Modern cosmology rests on extrapolation. We trace the expansion backward until density and temperature rise beyond comprehension, and then we stop. But what lies beyond that limit? Some physicists suggest the Big Bang was not an explosion but a transition, from one quantum state to another. The boundary we call the beginning could be fuzzy, emergent, or even cyclic. In quantum cosmology, space-time itself may have condensed from a pre-geometric phase, where time had no direction and causality did not yet exist. If so, the earliest light we now observe might come from fluctuations that predate space-time as we know it, echoes from before time began. Such ideas blur the distinction between physics and philosophy. If time has no true origin, then older than the Big Bang may not be a contradiction, but a clue. The light detected by James Webb, those red, ancient whispers, could be remnants of an earlier rhythm of creation still resonating within this one. A cycle of universes, each giving birth to the next. A continuity where beginnings and endings dissolve into one another. It is a notion both humbling and beautiful, that the cosmos may not have begun, but is instead forever unfolding, its history a continuum rather than a genesis. And so, as scientists model, speculate, and argue, the question remains suspended in the dark. What if the Big Bang was not the start of everything, but merely the latest chapter in an eternal book whose first pages have yet to be found? In the deep silence of space, discovery is a patient art. The questions raised by the Webb telescope's first glimpses of impossible galaxies did not end with astonishment. They began a new kind of pursuit, one that would demand every lens, every mirror, and every simulation humanity could conjure. Across the world and above it, instruments turn toward the ancient light. The James Webb Space Telescope continues its deep field campaigns. JWST, Sears, Uncover, each one a window carved into the earliest pages of time. These surveys stretch beyond the limit of sight, gathering faint red whispers from when the first galaxies were no larger than a thought. Through the NIR-SPEC spectrograph, every photon is dissected, its wavelengths revealing the chemical stories within. Hydrogen lines whispering of youth, oxygen and carbon betraying the touch of older stars. MIRI, Webb's mid-infrared eye, looks deeper still, into the dust that obscures, the warmth that remains when starlight fades. Each instrument functions as both archaeologist and poet, unearthing and interpreting the relics of creation. Beyond Webb, the Atacama Large Millimeter, Sub-Millimeter Array, ALMA, listens from Earth's driest desert. It does not see light as humans do. It feels the faint thermal tremors of cosmic dust and molecular gas. Within those signals lie traces of oxygen, O3, carbon, C2, and the delicate molecules that cooled the first galaxies into being. Where Webb reveals form, ALMA hears structure, the invisible scaffolding of the young universe. Together, these instruments are painting the same scene in different colors. Webb shows the luminous bones of galaxies. ALMA fills in their breath and dust. Soon, the new generation of extremely large telescopes, ESO's ELT, the Giant Magellan Telescope, the 30-meter telescope, will rise from deserts and mountain plateaus. Their adaptive mirrors, vast as cathedrals of glass, will peer into the same faint red-shifted light, refining spectra, resolving shapes, and weighing the stars within those primordial smudges. It is a global orchestra of observation, a symphony of instruments spanning from infrared to radio, each contributing a piece to the puzzle of time. Yet even this grand alignment of technology may not be enough, for what Webb revealed were not final answers, but the edge of a deeper map, one that future telescopes are already being built to navigate. NASA's Nancy Grace Roman Space Telescope will take the next step outward. Where Webb's gaze is narrow and deep, Roman's will be wide and sweeping, surveying thousands of galaxies at once across vast cosmic fields. Its sensitivity to near-infrared light will make it a hunter of the rare and the distant, cataloguing the early structures that Webb can later study in detail. The European Space Agency's Euclid mission joins in this quest, mapping the geometry of the universe itself. Its wide-field lens will trace the subtle distortions of gravitational lensing across billions of light-years, revealing how matter, both visible and dark, has sculpted the cosmic web. Together, Euclid and Roman will provide the coordinates, Webb and ALMA will provide the magnifying glass. But the horizon of instrumentation extends even further. The proposed Origins Space Telescope would look where no human eye has yet lingered. The far infrared domain, where cold dust and nascent stars whisper their first heat into the void. With sensitivity 1,000 times beyond previous infrared missions, it could see the chemical breath of galaxies in their infancy. Oxygen lines, water vapor, the smoke of creation itself. Meanwhile, a revolution is brewing at longer wavelengths still. Across the South African desert, the hydrogen epoch of Rayonization Array, HERA, listens for the faintest radio murmurs of hydrogen. The 21-centimeter line that pervaded the universe before the first stars burned it away. Soon, the Square Kilometer Array, SKA, will extend this listening power across continents, mapping the Rayonization of the cosmos in exquisite three-dimensional detail. Through these experiments, scientists hope to reconstruct not just when the first galaxies appeared, but how they illuminated the darkness. Every frequency becomes a form of archaeology, every map, a fragment of the universe's autobiography. And beyond the horizon of current imagination lies the dream of space-based interferometers, vast arrays of satellites linked by light, forming a virtual telescope the size of the moon's orbit. Such a network could resolve cosmic structures with the precision of divine vision, tracing the ripples of gravity and the shimmer of stars from the first dawn. For now, these remain blueprints, ambitions written in starlight. But their purpose is clear: to chase the mystery that Webb has uncovered, to follow it until the beginning itself yields its truth. While telescopes stare outward, another universe unfolds inward, inside the glowing cores of supercomputers. Here, in the hum of circuitry and the whisper of cooling fans, cosmologists recreate the cosmos from first principles. Every particle of gas, every grain of dark matter, every photon that escapes into the expanding void is simulated in exquisite precision. These hydrodynamic simulations, Illustris TNG, Renaissance Blue Tides Fire, extend deeper into time than ever before, exploring what conditions could yield galaxies at redshifts beyond 15, perhaps 20. Within these digital universes, gravity pulls, gas cools, stars ignite, and feedback roars. Yet even here, the early galaxies remain elusive, often forming too late or too faint to match Webb's revelations. To close that gap, physicists tweak the parameters, the cooling efficiency of primordial gas, the opacity of molecular clouds, the behavior of dark matter itself. Each simulation becomes a hypothesis made visible, a controlled dream of creation. Beyond simulation, the laboratories of Earth test the nature of matter itself. Cryogenic detectors probe for dark matter interactions. Particle accelerators like CERN's Large Hadron Collider push against the limits of known physics, searching for hidden sectors that might rewrite cosmic history. Statisticians refine Bayesian models to test whether the observed galaxies are genuine outliers or simply the product of cosmic variance. Teams compare data across instruments, correcting for background subtraction errors, gravitational lensing magnification, and photometric biases. Every anomaly must survive this crucible of doubt before it can be believed. The process is both humble and heroic, a collaboration across continents, where astrophysicists, data scientists, and theorists synchronize their work like constellations in intellectual orbit. Each dataset becomes a star in a larger map of understanding, and through this collective effort, the truth begins, slowly, stubbornly, to coalesce. Science is not content with mystery. It demands prophecy. Every theory, no matter how audacious, must offer predictions, signatures written in the light of the cosmos that can be tested, falsified, or refined. If the early galaxies truly formed from exotic cooling mechanisms, then their spectra should reveal peculiar fingerprints, unusually low metallicities, faint traces of molecular hydrogen, and elemental ratios inconsistent with later star generations. If primordial black holes shaped them, their clustering patterns would differ, tighter, more compact, following the gravitational wells of unseen masses. Dark matter modifications would leave subtler marks, deviations in small-scale structure, unexpected patterns in gravitational lensing, or distortions in the reionization timeline seen by 21 Symmetra surveys. Astronomers are already searching. Webb's next deep field programs target even higher redshifts, Z15, perhaps even Z20, where, if galaxies truly exist, they would predate the known cosmic dawn by hundreds of millions of years. Finding one would be like catching the echo of a universe still forming its first breath. Meanwhile, data from the cosmic microwave background, from Planck to future missions like CMB-S4, act as anchors. Every early galaxy must still fit within that thermal relic, its distribution of matter, its fluctuations, its silence. If it does not, the entire cosmological model will need revision. In this pursuit, the line between observation and theory grows ever thinner. Each discovery becomes both question and test, and each failure to reconcile them becomes an invitation to deeper wonder. Epilogue: from the deserts of Chile to the void beyond the moon's shadow, humanity has scattered its instruments like seeds across the dark. Each one listens, each one waits. The mystery of galaxies older than time has drawn the scientific world into a new era, not of certainty, but of exquisite doubt, and in that doubt lies possibility. The tools of this age, mirrors of gold, dishes of aluminum, simulations of code, are not just machines. They are extensions of curiosity itself, reflections of an ancient need to know what came before the beginning. Somewhere, between Webb's golden mirrors and the whispering hydrogen of Hera, between code and cosmos, lies the truth. And when it comes, it may not rewrite the universe. It may reveal that it was always stranger, deeper and more beautiful than anyone had dared to imagine. The universe has always demanded humility. Every discovery that pushed the horizon back has revealed not the edge of knowledge, but another vastness waiting beyond it. And now, as light from galaxies seemingly older than the Big Bang reaches our instruments, that humility deepens into awe. If time itself is questioned, if the great beginning we have believed in was not the first, then the story of existence is no longer linear. It becomes a tapestry without borders, a rhythm without origin, a silence endlessly unfolding into sound. For centuries, humanity has sought the beginning as if it were a crown, the ultimate answer, the first cause. The Big Bang was not merely a theory. It was a promise of closure, a comfort in knowing there was a moment when everything began. But now, that comfort trembles. The data does not lie, yet it hints at something that cannot yet be named. To stand before that possibility is to confront the limits of understanding itself. Perhaps these galaxies are illusions, misread signals, statistical outliers, errors waiting to be corrected. Or perhaps they are the footprints of a universe that never truly began, one that renews itself in endless cycles of expansion and collapse. If so, the cosmos is not a birth but a breath, exhaled and inhaled across eternity. In this light, the phrase "older than the Big Bang" ceases to be paradox. It becomes poetry. Time, after all, may be less a river than a sea, its waves colliding, overlapping, dissolving into one another. The moment we call the beginning might be just one crest among infinite others. Every new observation carries the scent of hubris and the echo of wonder. Humanity has believed itself to stand at the summit of cosmic comprehension, gazing backward toward its origin and forward toward its fate. Yet perhaps we are not at the summit, but on the first step of a staircase that ascends into forever. Science, in its truest form, is not the conquest of mystery. It is its continuation. Every equation, every telescope, every question whispered into the void is an act of reverence. The cosmos does not yield to certainty. It invites curiosity, and in that invitation lies meaning. If time is emergent, if it blooms from deeper hidden laws, then the universe before the Big Bang might not be a contradiction, but an inevitability. Quantum cosmology hints at fluctuations, vacuum births, and eternal inflations, cosmic foam from which our own universe could have bubbled forth. In such a reality, there is no singular beginning, only transitions between states, only awakenings from earlier dreams. The Webb telescope, and those that will follow, have not merely shown us light from distant stars. They have shown us the humility of our models, the fragility of our certainties. For even now, in the face of data that seems to reach beyond the beginning, we are reminded, nature writes the story. Humanity only reads the latest draft. Perhaps this is the true beauty of science. Not its answers, but its willingness to be rewritten. Not its pride, but its patience. Out there, in the deepest field Webb has ever captured, there is a single red dot. It is smaller than a speck, dimmer than a dying ember. Yet it carries the memory of an age older than time as we know it. That photon left its home when galaxies were young, or before galaxies even were, and crossed the emptiness of billions of years to reach a mirror of gold, floating in darkness, above a small blue world. Its journey is a message, a reminder that knowledge is never an end, but a path that folds back upon itself, leading always further. So the image remains, a faint red light, a whisper from the frontier of understanding, still arriving, still speaking, still urging the universe's children to listen more deeply. And as the final frame fades to black, the question lingers like a pulse in the void. What lies beyond or before the beginning?